I think it looks, I have not looked at it, so I think it looks similar. 46 on 353.
It looks to be the same sort of thing.
I think so. 46 on 353. Can you see? I know it's crooked, but it's set for the other camera that is next to this one, and I can't make both of them be straight. Sorry.
It's fine.
Suppose that f is continuous. F continuous on the interval 0, 4. We are told that f of 0 is 1. We are also told that f prime of x is bounded between 2 and 5 for all x in the interval 0, 4. Show that f of 4 is bounded by 9 from below and 21 from above. I have to close this book and take it away from here because I don't have enough room. Okay, perfect. So we're told that the function is continuous on the closed interval, and this is the first hypothesis of the mean value theorem. The second hypothesis is that the function is differentiable between 0 and 4. It does say that. How do I know? The function exists, the derivative exists, and is between 2 and 5. It must exist. So the function is differentiable on 0, 4. From 1 and 2, by the mean value theorem, we know that there exists a c in the open interval 0, 4 such that what?
Where f prime of x is equal to 0.
F prime of c. Careful. That's the Rolle's theorem. So let me refresh your memory. No, I just tossed them in the trash.
Oh, I see. The f prime c is equal to f of b minus f of a.
Yes.
Over b minus a.
Exactly. So the mean value theorem has only two hypotheses: continuity and differentiability. Doesn't say anything else. So therefore, we only have continuity and differentiability. So we can talk about Rolle's theorem. Exactly. So this, by definition now, based on mean value theorem, I will write what?
F of 4 minus f of 0.
Excellent.
Over 4.
Yes, minus f of 0 divided by 4 minus 0. Exactly, that's it. So then, I am told that f of 0 is 1. So I will write that, and first of all, and secondly, I know that f prime of c or f prime of x, for any x in the interval 0, 4, at all times f prime is squeezed between 2 and 5, or bounded. F of 4 minus 1 over 4 less than or equal to 5. Is this okay?
Yes.
So then, next step, can anyone tell us what to do? Anything?
Multiply both sides by 4.
Exactly. So 8 less than or equal to f of 4 minus 1 less than or equal to 20.
Add both sides.
Right. And that's exactly what we needed to find.
Okay. I see.
And this is it. Better?
Yes. Okay, great.
Perfect.
Thank you very much.
Anytime. Thank you. Anything else? Is there anything else we need to work on before we move on? Anything else? Other questions, WebAssign or otherwise? Anything? Anything? Critical numbers? Anything? max min, closed interval. Okay, well in that case let's move on to section 4.3. Section 4.3 deals with one of them we already talked about, the first derivative test. So we're going to look at the first derivative test and the second derivative test. So the title is how derivatives affect the shape of a graph. No, I really disagree with that. Would like to call that differently. Of course, it's not important. So 4.3, what we learn. Oh no, I forgot to turn off my phone. Crystal, I'm in class. I'll call you when I finish. Sorry. Bye. I'm going to turn it off now. It's off. Okay, so what we learn from f prime and f double prime about a function. If you want the graph, but in general about the function. So what we learn from the first derivative and the second derivative of f of x about f of x. So that's what the title should be. The first derivative and the second derivative don't affect the graph. We learn something from them about the graph. So I disagree with that definition. Okay. I would like us to just remember what we learned about the first derivative. So the first derivative we know teaches us or shows us about f of x what? Number one, increasing or decreasing intervals. So when the first derivative is positive, the function is increasing. When it's negative, it's decreasing. So this is one thing that we learn from the first derivative about the function. The second thing we learn is max min. Of course, local. Max, local, min. So this is what we learn. And I would like to start with the function. So I'm looking at what I chose yesterday. So you have, so this is the class from yesterday, and we chose 10, so I'm not going to choose 10. So you have more than one example. So yesterday was 10. This time let's look at a rational function. Number 12 on page 298. I'll copy the function, then I'll tell you what it says, what the problem is asking us to do. X divided by x squared plus 1. Find the intervals on which the function is increasing, decreasing, local max, local min, and something that I haven't mentioned yet, but we will. Okay, so in order to find increasing intervals or decreasing or local max, local min, I have to find the first derivative. So let's find it. I have to differentiate as a quotient. The numerator prime is 1 times the denominator minus the numerator times the denominator prime, which is 2x. So then the numerator becomes x squared minus 2x squared, so negative x squared plus 1 over x squared plus 1 squared. Now, I hope you're getting into my habit. I want that out, and you know why. I don't like negative leading coefficients, and it makes my life easier if I take that out. And of course, I will factor the numerator. At this point, I'm ready to start working on my table. If you don't like this table, I repeat myself a lot, I know. Use any table you want, but summarize the information somehow, otherwise you make it difficult on yourself. So, This is the table we've seen so many times already. I have an extra row now. And I promise this is the last row we are going to add. The second derivative. I haven't mentioned anything about it yet. I look at this function and I realize that the domain is all real numbers. How come? X squared plus 1 is never 0. Then I proceed to find the critical numbers. So when I set f prime equal to 0, I know that a fraction is 0 only when the top is 0. The bottom cannot be 0, it will be undefined, but in this case it's not possible. So only the numerator can be 0. So when I set x plus 1 times x minus 1, which is the numerator, that's why I factored it, I get positive 1, negative 1. In the correct order, negative 1, 1, 0, 0. So now I need to study the sign of the first derivative. Just for the purpose of the studying of the sign, I do not need the denominator. How come? It's all positive. I'm not going to waste my time on that. So I'm only looking at this with a negative. So I know that this is a quadratic function with a negative leading coefficient, so it has to have a maximum, and it crosses at negative 1 and 1. In between, it must be positive. Outside must be negative. You can say, show me again, and I'll do this. If you want me to show you, I'll say, let's plug in 0. 0 minus 1, negative 1, times negative 1, positive. Let's plug in 10. 10 squared minus 1 with minus is negative. Let's plug in negative 10. Negative 10 squared minus 1 with minus is negative. At this point, I will plug in the function these two values. When I plug in negative 1 here, the denominator is 2, negative 1 half. When I plug in 1, I have 1 half. So negative 1 half and 1 half. I also would like to determine these. These are the limits at negative infinity and infinity. Because I want to complete the table, and you'll see we will always do that. So I want to find a limit of x over x squared plus 1 when x approaches infinity, and then when x approaches negative infinity. Can anyone tell us how to proceed? Anything? Well, I hope you're there. I hope someone is listening. So if you plug it in, you'll have infinity over infinity. If you'd like to, let's refresh our memory on L'Hopital's rule. So then limit, as x approaches infinity, differentiate the top, differentiate the denominator, and now it's obviously 0, which we knew. Whenever in a rational function, the degree of the numerator is smaller than the degree of the denominator, the end behavior is always 0. Which means y equals 0 horizontal asymptote. At this point in time, I am trying to, first of all, before I proceed, I need to make sure that these two rows go in sync. This is the moment I catch my mistakes. And now let's see. From 0 to negative 1 half, the function is decreasing. Is that supported by the sign of the derivative? Yes, it is. The function from negative 1 half to 1 half is increasing. Is that supported by the sign of the derivative? Yes, it is. From 1 half to 0, the function is decreasing. Is that supported by the sign of the derivative? Yes, it is. Now, the problem is asking us to find intervals of increasing and decreasing. You do not have on paper, for me, you do not have to write them again. Because you told me. You're showing me that the function is decreasing between these two, union between these two. So between negative infinity and negative 1, union 1 to infinity, the function is decreasing. You don't have to write it on the side. But this is, if you're asked to, this is what I would write. F increasing on only open intervals, no brackets, and F is decreasing on negative infinity, negative 1, union 1 to infinity. But there is no need. If you summarize the information in the table, this is sufficient for me. Okay, now we need to identify the second thing that the first derivative is helping us with, max min. So this is a typical situation. This is a typical situation for a minimum. So this is local min, and this is a typical situation for a maximum, local max. I exhausted the first derivative. There is nothing else I can learn from it about the graph. So finally, let's look at the second derivative. First, let me tell you what it teaches us or tells us about the function, and then we'll go back to our function. The second derivative teaches us also two things. One, intervals of concavity. I'll explain. And the second one, inflection points. Point or points. Okay, so let me give you an example, and we'll come back to our function. I would like to look at, as an example, f of x equals x cubed. So here's the graph. We use this a lot, and in other classes. Notice that the cross is not like this. The solution x equals 0 has multiplicity 3. That's why it's a slow cross, not a straight cross. Okay, so if I find the first derivative, when I find the first derivative, calculate the first derivative, I get this. Obviously, no max min. No max min. How come? Because it's always positive. It doesn't change sign. If the first derivative never changes sign, there is no max min. Here it changes sign, it has a min. Changes sign, specifically, max. But this one is always positive, so there is no max min. So let's find the second derivative now. That's 6x. Okay, to the left-hand side, see what happens? The derivative, the second derivative, is less than 0, to the left of 0. And the function is concave down. Concave down, opening down. Then, so the second derivative negative, function is concave down. Second derivative positive, which is to the right hand side of 0, when x is greater than 0, 6x is positive. You see, the function is concave up. This is what we mean by intervals of concavity. For this function, between 0 and infinity, the function is opening up. For this same function, between negative infinity and 0, the function is opening down. Concave up, concave down. Okay, what is this? It's exactly this point where the second derivative is 0 or undefined in certain situations when the function is defined, and the second derivative changes sign. Because if it's 0 but it never changes sign, it doesn't change sign at that point. There is no change in concavity and there is no inflection point. So this point is the inflection point where the function changes concavity. From opening down, at this point, changes into opening up. This is what we learn from the second derivative about the function. That's what it tells us. Okay, so now back to our function. We have to find the second derivative. Where is my first derivative? Here it is. I'm not going to differentiate this, I'm going to differentiate this. So, and I am on page 4. So I'm going to copy the derivative so I can put those pages away for now. Okay. So we have the first derivative. We want to determine the second derivative. Leave the negative outside. Can wait patiently. Put x squared plus 1 to the 4th power because we have to square that. Now the calculations become a little bit hairy, but that's okay. The numerator prime. Always stop me if you need more time or if you have a question.
I'm sorry. On your previous, when you were explaining the implications of the double prime and the second derivative, you said that for the first derivative, it does not indicate a maximum or a minimum for 3x squared. How is that possible? Because there would be a minimum value if you put x was 0, just 0. And that would be the smallest value for that function, right?
Very good point. Okay, let me explain. I'll come back. Very good question. So we want to look at, again for a moment, at x cubed, right? So here is my table. F prime of x, f of x, and the second derivative. Obviously, the domain is all real numbers. It's a polynomial function. So I know that when x is 0, the function will be 0. We know that, right? So we determine the first derivative as 3x squared. We set 3x squared equal to 0. We get basically two solutions and both are 0. So it's 0. And now I need to study the sign of the derivative. If I plug in negative 10, I get positive. If I plug in positive 10, I get positive. Which guarantees that the function is always increasing. If a function is always increasing, it could never ever have a max or a min. Because if a function is always increasing, if it doesn't turn to become decreasing, it will not have a max. So it has to turn. So here the slope or the derivative is positive, but here the derivative is negative. But this doesn't happen here. And if you look at the graph, follow my marker, and tell me when the function is decreasing. The answer is never. Since it's never decreasing, it could never have a max or a min, even if it has critical numbers. Critical numbers may change into max min, not necessarily. In this case, the function has a critical number, 0. But the derivative never changes sign. If it never changes sign, the function cannot have max min. So, very good question. Let's go back to what we did last time, one more time. I keep getting this out of my trash can. It's recycle, of course. Okay, so if the first derivative, even if there is a critical number here, if it's always negative, that's not a max min. Even if there is a critical number in here, whatever that is, if it never changes sign, it's always positive, there is no max min. Is that better?
Yeah, I think I understand that. But even in these instances, you couldn't define the minimum as negative infinity, but the maximum is positive.
Oh, we cannot define max min as infinities because I have to be able to give you the ordered pair. If I can't give you the ordered pair, there is no max min.
Okay.
I can say, go and look for it towards infinity. There must be a maximum somewhere. Is that clear?
Yeah, I think I understand this. Okay, thank you.
Thank you. I think I'm going to make this one 4. And I'm going to make this one 5. Okay. So, where was I? So, the numerator prime is 2x times the denominator minus the numerator times the denominator prime. Careful here. 2 x squared plus 1 to 2 minus 1 times the inner function prime. Okay. Can anyone tell us what is the key step here now, without which I can't really continue? And we did this a lot when we differentiated these functions.